Welcome back to Math 104. We begin video set number 6. Thus far in the course, we've focused on experiments with equally likely outcomes. For these experiments, our approach to finding the probability of an event has been to compute a certain fraction. The numerator of this fraction is the number of outcomes in the event, and the denominator in this fraction is the number of outcomes in the sample space. In other words, the number of different possible outcomes of the experiment. This approach makes every probability computation a matter of solving two counting problems. We are first counting the number of outcomes in the event itself. We are then counting the number of different possible outcomes of the experiment. Only after we've solved this counting problem and solved that counting problem do we divide. We've been thinking about probability this way for so long it seems obvious. So what other approach could there be? We're going to introduce a new approach, and to warm up for it, let's look at a basic example of what we've been doing. So by our usual thinking, if you flip a fair coin twice, the probability of one head and one tail in any order equals the number of outcomes in the event, that's 2 choose 1. That entry of row 2 in Pascal's triangle counts the number of ways this event can occur, divided by the number of outcomes in the sample space. That's 2 squared. That's from the multiplication principle of counting. So we count the number of outcomes in the event, that's 2. We count the number of different possible outcomes of the experiment, that's 4. So our probability is 2/4 or 1/2. Now what else could we do? Another approach to multi-stage experiments is to think of each stage as having a probability. So tree diagrams are very helpful here. Let me draw this horizontally because it's a little bit easier. At the first stage, there could be heads or tails. I'm going to label each edge of the tree with the probability associated with it. So at the first flip, there is a 1/2 or 0.5 probability of heads, and there is a 1/2 or 0.5 probability of tails. At the second stage, I can again obtain heads or tails, again with a probability of 1/2 for either one. If the first flip was heads, then the second flip could be heads or tails. If the first flip was tails, the second flip could be heads or tails. We're working with a fair coin, so again we label each edge with 1/2. Notice how we're setting things up so that even if the coin were unfair, we would know how to account for that in the way we do the labeling. Now, what is the probability of one head, one tail in any order? Well, I have an outcome here, heads followed by tails. That contributes towards my event. And another outcome here, tails, heads. That also contributes toward the event we're looking at. The probability of heads, tails equals, and this is the crucial new idea, 1/2 times 1/2. Why times? Because when we perform this experiment, at stage 1, half the time we'll get heads. Having obtained heads on the first flip, half the time we will end up with heads followed by tails. How often do we get heads, tails in that order? Half the time. And how often do we get tails, heads in that order? That too is happening half the time. Thus the overall probability, or the total probability of our event, that there will be one head and one tail in any order, equals the sum of these two probabilities, the sum of the probabilities of the outcomes that contribute to it. So 1/2 times 1/2 plus another 1/2 times 1/2. In other words, 1/4 plus another quarter equals 2/4. We obtain exactly the same result by this thinking as we did by our usual method of counting. The new thought process here is that the probability of a single outcome is the product of the probabilities associated with the stages along the way towards obtaining that outcome. And then, as before, the probability of an event equals the sum of the probabilities of the individual outcomes contributing towards that event. One very significant advantage of tree diagrams and multiplying probabilities at successive stages, rather than counting, is that now we can understand experiments with unequally likely outcomes. There are very many of these in real life. It would be too confining just to look at experiments with equally likely outcomes, so now we will have a much broader range of applications. Here is our first example. Suppose that at the shooting range, you hit the target with probability 0.7 on each shot. You take a total of 3 shots. What is the probability of exactly 2 hits and 1 miss in that particular order? To appreciate what's going on, let's draw a tree diagram. Stage 1 of this experiment is to take shot number 1. That has probability 0.7 of a hit and 0.3 of a miss, which I label on the edges of the diagram here. The branching from this result of stage 1 looks exactly like the original branching into either a hit or a miss, the hit with probability 0.7 and the miss with probability 0.3. Similarly, if there is a miss at stage 1, what could happen next? Either a hit with probability 0.7 or a miss with probability 0.3. This gets a little bit harder to draw as we reach stage number 3 of the experiment, but it's the same idea that each successive branching looks the same as any other. No matter what has happened previously, on the next shot, there is a 0.7 probability of heads and a 0.3 probability of tails. For thoroughness, label each of these edges in the tree diagram by the associated probability. For what event are we asked to find the probability? It's the event consisting of just one outcome: hit, hit, miss in that order. There are 8 possible outcomes of this experiment, 8 possible paths from the start of the tree to the end, 8 possible 3-letter words consisting of H's and M's. Our event consists of only one outcome. The probability of that one outcome, the probability of the word HHM, by the same thinking as in our previous example, equals 0.7 times 0.7, so 70% of 70% of the time we're getting hit followed by hits, and then 30% of 70% of 70% of the time, that continues on to hit, hit, miss. I'm writing these multiplications just by writing the numbers in parentheses next to one another without the time symbol, because it's going to get very cumbersome to keep writing it. It turns out that this equals exactly 0.147. That is the probability of getting hit, hit, miss in that specific order. Our important follow-up question is, what is the probability of exactly 2 hits and 1 miss in any order? 2 hits and 1 miss in any order is an event with 3 separate outcomes in it. There is the probability of hit, hit, miss that contributes towards the likelihood of this event. We already found that to be 0.7 times 0.7 times 0.3. But there's also hit, miss, hit. That too contributes towards the event. We must consider the probability of hit, miss, hit, and that is 0.7 times 0.3 times 0.7, so following along the tree here, 0.7 times 0.3 times 0.7, 70% of 30% of 70% of the time, you get specifically hit, miss, hit. And finally, miss, hit, hit is another outcome which is in this event, which contributes towards the likelihood of this event. How much does it contribute towards the likelihood of this event? It contributes 0.3 times 0.7 times 0.7. 30% of 70% of 70% of the time, you will obtain the outcome miss, hit, hit. How do we know that those are the only outcomes that contribute towards this event? We can either look through the tree and look through all the outcomes, hit, 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 no, that doesn't contribute, hit, hit, miss, yes, that does, hit, miss, miss, no, that is not in our event, miss, 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 that is really not in our event. We could go through one by one through all 8 outcomes, all 8 ways of reaching the end of stage 2. Or we can go back and realize that based on the work we've already done earlier, we know how many words there are. The number of 3-letter words with 2 of one letter and 1 of the other letter equals 3 choose 2. So Pascal's triangle has not gone away. What then is the probability of our event? The overall probability or the total probability of 2 heads and 1 miss in any order? It is the sum of the probabilities of the individual outcomes. I'm going to write them out in gory detail first, and then we'll notice the crucial observation. These are actually 3 copies of the same number. Right? 0.7 times 0.7 times 0.3 is equal to 0.7 times 0.3 times 0.7. Again, we are grateful to live in a universe where multiplication is commutative, so that even though these are 3 separate outcomes, And even though we're looking at an experiment with unequally likely outcomes, these three particular outcomes are equally likely to one another. What we really have here are three copies of 0.7 times 0.7 times 0.3. Or if you want to write this in a way that reflects the fact that row 3 of Pascal's triangle knows how many separate outcomes there are in this event, we can write 3 choose 2 times 0.7 times 0.7 times 0.3, or 3 choose 2 times 0.7 squared times 0.3. When we compute, this equals 0.441. There is a 44.1% chance that in 3 shots at the target, exactly 2 of them will hit and 1 will miss. Before going on to the next video, find the probability of at least 2 hits by drawing the tree diagram and reasoning out the probability as we have just done.